thing in history.
It's in bird now.
Not really, but change. Hey, guess what? We're staying with our rates of change theme. What does that mean? Derivatives. Velocity, slope. Yes, yes, yes. Okay, you're good. If that's funny. If I drive to Denver, it's 180 miles from Parachute to Prescott. I have a fiance that lives in Denver. I live here sometimes. It takes me 3 hours. What was my rate of change? Average rate of change. Okay. Okay, my rate of change, 60 miles an hour, right? Okay, now, what if anybody realizes speed? Is there anybody? Okay, Michael Lewis. So this is Mr. Arthur, and this is Mr. Lewis. Okay, he goes to Denver, and it's 180 miles. Yeah, that's good. That's not too bad. Benefit of the doubt. I'm not sure if it's I know. What's his rate of change? 90. Okay, well, let's put an A on there for average. Okay. If we left at the same time, how much faster is he traveling? He gets there an hour earlier, but how much faster is his rate of change? Okay. Yeah, he's going 30 miles an hour faster. Okay. So if we leave at the same time, he is going that much faster. Okay. That is called related rates. We have just related two different rates, right? That's a related rate. Okay. Basically, we are comparing two rates of change. Okay. In this case, it's easy because it's a linear subtraction problem. Like I said, these can get very, very nasty. This is the concept. Okay. You understand that? Okay. Not too long. Thank you. Yeah. Stand over there, you stand over there. Okay. They're each going to be walking at their own rate, correct? Walk together. Go on each other. Now, we can relate their rates, correct? So that'll be a linear example where their rates are changing with respect to each other. Okay? Stand over there. You stand there. I want you to walk that way. Is that linear? This is not linear anymore, is it? So how are the rates changing with respect to each other? Okay, these are the types of things that we're going to start to investigate. What shape do they make? And what makes it? If you connected the two of them, what shape is that? A triangle. So guess what theorem we would probably use? Pythagorean theorem. I did. Okay. Here's a classic related rates problem. It's called the sliding ladder problem.
This is one where it's like it's on a house and it's down.
Yes, we have a ladder. Leaning against the wall. Okay. The ladder is 5 meters tall. The bottom of the ladder is 1.5 meters from the end of the wall at time 0. Because we have time here involved now. You're used to working with static numbers. Now we're throwing time in. Okay, it slides from the wall, slides away. .8 meters per second. Find the velocity of the ladder, the top of the ladder, at t equals 1. Okay, now velocities, we've got signs to deal with here. Top of the ladder at t equals 1. So, ladder slides out, top comes down, right? How fast is it going down? So, here's how we tackle these problems. What? This is a Pythagorean theorem question, right? Right triangle? Pythagorean theorem? This is a Pythagorean theorem linear. X squared plus y squared equals z squared. That's why. We're changing by squares and not in a linear fashion. So, here's how we tackle this. You ever heard of a certain restaurant called Fiat Chains? Yeah, right? See, when you're doing AP calculus, then you get to think of this Fiat Chains restaurant. Okay, this is like that. It's a way for us to solve these problems. Okay? It's called PF chain F. What? Okay, this is the way we're going to solve these. This means you draw a picture. That's an app. What did you see an app before? Yeah, it's on Twitter. This is the formula for the shape that you're dealing with. Okay, this is the change. And this is at that moment or time. Okay. I like to do this draw like you do. So what's my picture? Right triangle, right? And label it. This is at t equals 0, correct? The question asks for time 1. How big is this gap at time 1? Okay. Start 1.5 in 1 second, that's 0.8. Right? 0.3 meters at time 1. What's time 2? 3.1. to another point. Alright, so that's all the information we have. We'll assign variables here in a minute. Okay. Formula. So what variables do we have here? X, Y, Z. What's the formula? We're doing the size of the shape, right? So I'm going to set it. Formula. Leave space here. We need it. Okay. What does it change? Taking rate of change here. Okay, this is x, correct? Yeah. With respect to time. So that's where I'm going to write dx dt. It's the x variable that's changing with respect to time. It's a velocity. Distance over time, miles per hour, meters per second. Do we know dy dt? Okay. That's what we're looking for. I'm just going to write it down. That's going to be what we're solving for. Now, at that level, okay, this is time 1, right? At time 1, what is x? 1, 3, we already got it. What is z? It's always fine, thankfully, yes. Okay. And what is y? Okay, y, figure that out, right?
Y plus 1.
Okay, go calculate y. Pythagorean theorem. Square root of 25 minus 2.3 squared. Disagree. Okay, we have everything laid out as we need it. Anybody figure out why I can do this? It doesn't change. It's a constant, right? If it's a constant, I can plug it in. But if it's changing, like this distance and this distance, x and y are changing, we need to leave it. Okay, so that plug it in. So now we need to take the derivative. Implicitly, with respect to time. Okay, so what's the derivative of x squared? 2x. With respect to t, it's dx dt. This is the rate, right? With respect to time. Plus 2y dy dt. Okay? Equals 0. That's why I plugged it in. Nice. If you don't plug that in, you get 2z dz dt. dz dt is 0. Right? That's another way to reason through it. Is that dz that never changes. Okay. So that side's going to end up 0. Okay, maybe we'll see how to solve it. We are solving for, we've identified, plug in x, plug in dx dt, plug in y. We have all those numbers. And solve for dy. Yeah, it's a rate. How fast is the ladder moving? Right? What is x? What's dx dt? Positive 0.8. Y. 39. Wait, what? Because it gives us that. This is the x, right? How fast? 0.8 meters per second. So that is the change in the x distance with respect to the time of seconds. The x dt is 0.8. And that's what it is. Now solve for dy and dt. What is this plot? And this 8.7. 8.87. Right? So we subtract that over. And the line, right? We get 8.414. That's far enough. Include units. Distance. That's the rate. So what does that mean? Top of the ladder is time 1. At time 1, the top of the ladder is traveling 4.414 meters per second down. Right? So sometimes you have to interpret these. So this is very, very important. Settle down. Very important that you write these correctly. At time 1, not around. Okay? It has to be at. Specific. It's instantaneous rate of change. You have to be bam. Okay? The ladder. Sorry. The top of the ladder is traveling or moving 0.414 meters per second down the wall. Very specific. Why did I not put a negative here? Exactly. If I had put a negative and down, guess what? Okay. That's, you know how many points are missed every year they do this for this?
A lot.
one at least by a lot of people. I would recommend against it. They're looking for you to know. You can be a smart aleck, but they're looking for you. You wouldn't go to your boss and say, hey, we're traveling negative 10 meters per second in the westerly direction. He's like, what? No. 5 meters per second east. Okay? I'm gonna do it. Yeah, how would you know that? Okay, I don't have time to show you the other one, but it's example 4. So let's talk about it real quick. You got a person. This is a really popular one. Looking at a rocket. It's supposed to be a rocket. Which function am I going to use? It's usually the hardest part. If I'm given an angle measure, speed going up, distance from, this is the equation I would use. Right? Than is opposite over adjacent. You would do some work with that. The nice thing here is that x is the static, right? X is static here, so we would plug a number in. Y is changing, and theta is changing. But it doesn't change your method at all. You still draw a picture, you get your formula, you get everything that's changing, and what's happening at the moment. Draw it out, and should know what the derivative here, and you can solve it. Okay. No, you won't need the quotient rule because x is never changing. If you're 100 meters away, you just plug it in because that never changes. Okay. So that's just a brief look at that problem. I would love to show it to you. PJ, I want to show you example 2 and 3. Example 5 is when it gets hard. If you want to look at some harder ones. So let me give you the work. You can start on it. I recommend starting. Bring questions. I'm telling you to wait for number 1 till Tuesday. I'm giving it to you, but hold on. It's always really tense when I just keep writing. Yeah. Did I give you these yesterday? What did I give you? Did I give you 18 or 19? 3.9? Or, no, okay, I got it. Oh, I got written this recently for some reason. Some practice. Some, it has a 3, 5, 7, 9, 2, 1. I only gave you 6 new problems. Not until Wednesday. It's like 1 a day. So 16 problems. These should be getting faster.
So if you look through 3, 5, 7, and 9, identify the shape before you leave. Another clue, what shape is it? Circle. And part A asks you which form, tells you which formula to use. Yeah. Area equals pi r squared. So that only has one variable, r, and well, a and r. So that one's pretty straightforward. You take the derivative. Number 5. Use a sphere, and they give you the formulas. Most of the time, we're going to give you formulas. And that's the second circle, or Pythagorean theorem. 7, sphere, how about 9? The ladder problem. Number 9. You just have to deal with different numbers. Huh. So you're doing it time 2 instead of time 1. Okay? So I would start at 9 if I were you guys, or 3. 3 or 9 is easiest. Give those a try. And then, the 21 is going to be like the rocket. He survived no good to be dead. He survived the viral problems. But he survived. He is dead. Did he survive? Yes. He's in perfect hibernation. Y'all never get to move that. I don't know, maybe after the 5. Empire. Guess what is out now?